now we will start the 4th week of this course. In this week, I will continue the discussion on symmetry operations, and we will move to a different kind of symmetry called translational symmetry, which is only seen in crystals. Okay? And so in this week, I will be talking mostly about translational symmetry, and I will also give some idea about why we learn about symmetry operations, and we will also talk about how you combine various symmetry operations. So, in the first lecture of this week, that is this lecture, I will talk about combining symmetry operations and about translational symmetries. So, week 4, the first lecture, we will be talking about combining symmetry operations, and we will introduce the general idea of translational symmetries. So, let us recall that a symmetry operation is an operation that leaves the crystal unchanged, and we should keep in mind that it is an infinite crystal. Okay. So, the crystal extends to infinity in all directions. Okay. So, it is an operation that leaves that crystal unchanged. Okay. So, if you do a symmetry operation, you cannot distinguish the resulting crystal from the original crystal. Okay. So, now it is very obviously clear that if you do one symmetry operation and then you follow it with another symmetry operation, okay, then you will again leave this crystal unchanged. Okay. So, it is very obvious that a combination of symmetry operations will leave the crystal unchanged. So, a combination of symmetry operations is also a symmetry operation. So, what we mean by a combination of symmetry operation is you do symmetry operations successively. So, and we will see examples of this. Okay. Now, you can look at a combination of symmetry operations as some new symmetry operations. So, let me say that if you have a crystal, okay, let me show this in blue color, okay, and you do a symmetry operation. Let me call it S1. S1 is a symmetry operation. Okay. Then you get a crystal that is identical. Okay. Of course, I mean you have transformed it, but essentially you cannot tell the difference between the original and the final configuration. Okay. Then if you do another symmetry operation S2, okay, then again S2 will leave the crystal unchanged. So, overall the crystal will be unchanged. Okay. Now, but you did these two symmetry operations. Now, you can ask the question, can I do a single symmetry operation that corresponds to both these symmetry operations? Okay. Can I do a single symmetry operation? Okay. Clearly, to go from here to here, again you are leaving the crystal unchanged. So, it will be a single symmetry operation. Okay. And we express this relation as S equal to, so first you operate by S1, first you act by S1, then you act by S2. So, it is shown in this order. So, typically since the symmetry operation acts on the crystal, we can say that this symmetry operation on a crystal is equivalent to first acting by S1 and then by S2. Okay. So, now sometimes you can easily see what this symmetry operation is, what this combination of symmetry operation is. Sometimes it is not easy to visualize what this combined symmetry operation is. Okay. And a general way to look at symmetry operations and to see how the product of symmetry operations acts is to consider the effect of a symmetry operation not on the entire crystal, but on one point in the whole crystal. Okay. So, so for example, we are thinking of something like this, that if you have these coordinate axes x, y and z, okay, and you have some point somewhere in the crystal, okay, and this is a point in space, okay, and it is also a point inside the crystal. Now the crystal will have atoms everywhere. Crystal will have its atoms, whatever be the symmetry of the crystal. So these are the crystal atoms, okay. Now and this is one point somewhere in the crystal, okay. So in the middle of all these crystal atoms there is some point, some arbitrary point, okay, and we ask how this arbitrary point transforms on a symmetry operation. So what we are doing again is to take some arbitrary point, okay. The arbitrary point that we are considering will have coordinates x, y, z, okay. Now when we perform the symmetry operation on the crystal, then we will also perform it on this arbitrary point, okay, and this point will go somewhere. For example, suppose I do an example, okay. Let us say you have a symmetry operation of reflection about, let us say, y z plane, or y z plane. So if you reflect this point about the y z plane, okay, then you can see that what will happen is that and let me use the symbol sigma, then let me denote this by sigma y z, okay. So if you, so what we are saying is that if you take this operation, so this operation sigma y z, if you operate it on this symmetry point x y z, okay. So you take this point, okay. Now you can see that when you reflect this point about the y z plane, okay, then you will get a new point. So you are reflecting about the y z plane, which is the plane of the screen. So if you reflect it, then if this point is located above the screen of paper, it will go below the screen of paper, okay. So your new point will be behind the screen of paper, okay, if the original point is above the screen of paper, okay. And you can easily see that the new point, since you reflected about the y z plane, will have the same, this new point will have the same y z coordinates, but its x coordinates will be changed to minus x, okay. So its x coordinate will change to minus x, but its y and z coordinates will remain unchanged, okay. Now sometimes I mean especially in crystallography, we represent this minus sign as a x with a bar, y, z, okay, and we leave. So the minus x is represented as x with a bar. So what you can say is that this sigma y z operated on x y z gives you this new point, which is minus x y z. Okay. You can do this for other operations too. So let us take an example. Let us rotate this point by 180 degrees. About the, let us rotate it about the z axis. In this case, you can see what will happen. So if I take this point and rotate it about the z axis, okay, then this point, its x and y coordinates will not change, or rather its z coordinates will not change, but its x and y coordinates will change. So, if you rotate it by 180 degrees, C2 corresponds to rotating by 180 degrees about the z axis, then you can see that the new point will have the same z coordinates. Okay. Now, what about the x and y coordinates? Now, you can again see that the x coordinate will change sign, the y coordinate and the x coordinate will change sign. So, you will get x bar, y bar, z. Okay, they will have the same value, but they will change sign. Now, these are fairly simple to see. So, things like C2 and sigma etc. are quite easy. Okay. Now, let us take something that is slightly more difficult. Let us consider C3 acting on the z axis about the C3 that is located along the z axis acting on the point x, y, z. Okay. Now, a C3 operation corresponds to rotation by 60 degrees. Okay. So, you are rotating by 180 by 3, that is 60 degrees. So, if you take a point x, y, z and rotate by 60 degrees about the z axis. Okay. Now, we can see what will happen. So, first of all the z coordinate will remain the same. So, we will just leave the z coordinate as it is. Now, what about the x and y coordinates? Okay. Now, the x and y coordinates, to know what will happen, we will draw this picture slightly differently. We will show it in the xy plane. Okay. So, the z axis is coming out of the plane of paper, and let us consider a point. Okay. Now, the x and y coordinates of this point. Okay. So, we do not care about the z coordinate because it is remaining unchanged. So, if there is a point with coordinates x, y, z, then after rotation by 60 degrees, you can see what happens. So, you will have this point and you rotate it by 60 degrees, you will get some point that is this way. So, this looks more like, looks much larger than 60, I should take slightly smaller. So, you take something like this and you will get a new point that is located right here. Now, the question is, what is the relation between the coordinates of the original point and the coordinates of the new point? So, if this original coordinate had these coordinates, so x and y, so this distance is y, this distance is x. Okay. Now, this angle is 60 degrees, this angle is 60 degrees. Okay. Now, this new point has some new coordinates. So, this is the new coordinates, okay, the new x and y coordinates. Okay. Now, if you want to, it takes a little bit of work, okay, to work out the new coordinates. Okay, if you have to work out these new coordinates, you have to rotate by 90 degrees by 60 degrees and work out these coordinates. Now, this turns out to be a little bit more work, okay, but not a whole lot. Okay. So, the new point will have the following coordinates. So, you can work it out the following way. So, if you take this angle 60 degrees, okay, and you imagine that you drop okay, or you can eventually work this out and you will get something like this, x by 2 plus y root 3 minus y root 3 by 2. Okay. So, it is essentially x times cosine of 60 degrees minus y times sine of cos 60 degrees. Okay. The other other term is the y coordinate is x root 3 by 2 plus y by 2. So, that is x times sine of 60 degrees plus y times cosine of 60 degrees. So, you can use the general relation x cos cosine of theta plus y or minus y sin theta. This is x prime. This is for rotation by theta degrees about the z axis. Y prime, the new y, okay, is equal to x sin theta plus y cosine theta, and the new z is equal to the old z. Okay. So, you can see now this, since cosine theta is equal to cosine of 60 is half. So, you get x by 2 plus x plus y root 3 by 2, that is the new x coordinate. So, the new x coordinate is x by 2 minus y root 3 by 2. The new y coordinate is x root 3 by 2 plus y by 2, okay, and you can verify these fairly easily. New z coordinate is nothing but the old z coordinate. Okay. Now, this way you can work out all the symmetry operations. For example, if you invert about the origin, okay. So, if you do an inversion about the origin, so you are doing an inversion about the origin. So, using 0 0 0 as the point of inversion, and if you invert this point x y z, you can easily see that it goes to minus x, or write it in terms of, in the notation that we have been using, x bar, y bar, z bar. Okay. Now, this is very useful. So, this idea of symmetry operations on an arbitrary point is very useful, because now you can easily see the effect of combination of symmetry operations. So, you can do C3 followed by sigma. So, we can easily do C3 followed by sigma, okay, and what you will get is you will get you will suppose I do let me write it here. So, suppose I do C3 of z, okay, operated on I mean first sigma of y z, okay, that means first you do sigma y z, then you do C3. So, sigma y z will give you x bar y z. Now, C3 will take x y z to this. So, all I do is I just replace this by x bar, okay. So, I will get x bar by 2 plus y root 3 by 2, or minus y root 3 by 2, and then you get x bar root 3 by 2 plus y by 2, and you will get z. Okay. So, the only difference is that only difference from the C3 operation was that you replaced x by x bar, and that is a consequence of this sigma y z. So, basically you can easily combine symmetry operations, and you can find the effect of this combination of symmetry operations. Okay. Now, sometimes the combination of symmetry operations can easily be identified as another symmetry operations. So, I should emphasize that this is only sometimes easy to visualize combination of operations. Okay. So, let us take some examples, okay, and sometimes they are easy to visualize, sometimes they are not. Okay. Now, first thing is, if you take rotations about the same axis, okay, then you will get another rotation. So, for example, if you do a C3 followed by a C3, okay, two successive operations, okay, this will be denoted as C3 square, okay, which is same as rotation about same axis. So, if C3 corresponds to rotation about an axis by 60, okay, then C3 square corresponds to rotation about the same axis by 120 degrees. Okay, so C3 square corresponds to rotation by 120 degrees. Okay. Another example, suppose I take C2 x and I follow it by C2 y. Okay, suppose I take C2 x times C2 y. Okay. Now, what does this give? Okay. So, so now if I take C2, so let us consider an arbitrary point. So, let us consider C2 y times C2 of x operated on an arbitrary point. So, if I take C2 of x operated on an arbitrary point, then by the same thing we just saw, okay, this gives you, so the C2y is as it is. Now, I am just doing this part. So, this will give me x, it will keep the x coordinate same and it will change the y coordinate and the z coordinate. Okay. So, again the assumption, the C2y is C2 about the y axis, or C2x is C2 about the x axis and C2y is C2 about the y axis. Now, if I do C2y on this point x y bar z, it will keep the y coordinate the same and it will change the signs of the x and z coordinate. So, you will get x bar, y coordinate will be the same, it will change the sign of z bar of z bar. So, it will become back to z. Okay. And you immediately notice that here what I got is something that looks like a z coordinate is unchanged, but the x and y coordinate have flipped sign. So, what you can see is that this is nothing but C2z time operated on the original point. Okay. So, what we have shown is that C2y times C2x operated on this point is the same as C2z operated on this point. So, we can write the relation between the symmetry operations C2y C2x is equal to C2z. Okay. This is a very special case where we could easily see the relation between the rotations. Okay. And I should emphasize that you cannot always see this. Okay. And in this particular case we see easily that the combination of these two rotations is another rotation. Okay. Let us look at some other combinations. Okay. This is again a very well known example in molecular group theory. Okay. Suppose I take sigma of x z, okay, and I operate on it by some, let me choose C4, and the C4 is about the z axis. Okay. So, first I am operating by sigma x z and then by C4. Okay. Now, let me show it pictorially. Okay. So, we are taking sigma about the x z. So, I will show it on the xy plane. See, on the xy plane, the z axis is coming out of the plane of paper. Okay. So, sigma x z is essentially perpendicular to this. So, it lies along, let me show it in a different color. So, sigma xz is this. That means it is a mirror that is along the x axis and it is coming perpendicular to the plane of the paper. So, this is your sigma xz. Okay. Now, what I am doing is I am doing a succession of two operations. I am operating by sigma xz first and then operating by C4. Okay. Now, what do you get? Okay. Now, to do this, so let us consider an arbitrary point. So, if you consider an arbitrary point x, y, z, and you operate it by sigma xz, then follow it by C4. Okay. So if I do this operation, what I will get is, so I am just doing the second operations, I am just doing the second operation, that is this operation, which will be the first thing that will operate on this x, y, z point. Okay. And what you can see, it will keep the, so sigma xz, okay, we are reflecting about the xz plane. So, it will keep the x and z coordinates the same, it will just change the sign of the y coordinate. So, you will get x, y bar, z. Now, what happens when C4 acts on this point? Okay. Now, to do this, you need to know what is the effect of C4. Okay. C4 is rotation by 90 degrees. Okay. So, C4 will be rotation by 90 degrees. Now, cosine of 90 degrees is 0 and sine of 90 degrees is 1. Okay. So, what it will give you is, so it will be x times cosine of 90 degrees minus y bar, okay, times, because the sine of 90 degrees, that will be the new x coordinate. The new y coordinate will be x times sine of 90 degrees plus y times cosine of 90 degrees, and the new z coordinate will just be the original z coordinate. So, these will be the coordinates, and if you just go ahead and work it out, you will get minus of y bar. Minus of y bar is nothing but y, okay, and sine 90 is 1. Similarly, you have x sine 90, that is just x, y cos 90 is 0. So, you do not have to worry about that. So, you get something like this. Okay. So, you get something that keeps the z coordinate the same, okay, but changes the x and y coordinate. Okay. So, this combination of operations, okay, so this combination of operations keeps the z coordinate the same, but swaps the x and y. Okay. Now, the question is, what would be something that does this? Okay. And the answer is the following thing would do it. So, if you reflect about a mirror, okay, that looks like this. So, now this corresponds to reflection about a mirror, about this mirror. So, if you reflect an arbitrary point about this mirror, so I will just show it again. So, if you have an arbitrary point, okay, if you reflect it about this mirror, then you can see that the x and y coordinates will get swapped. So, the new point, okay, so if this was your x y and z, then this new point will have y x z. Okay. So, essentially what we identified is that C4 z into sigma x z, this is equal to sigma, and we will give this a name. This is in molecular group theory, this is given the name sigma d. So, we will just be consistent with that notation. Okay. So, it is a diagonal and it is actually it is perpendicular to the z plane. Okay. We do not need to bother about that, but basically we can do a common. So, what we are seeing is that a rotation followed by a reflection gives you this rotation. Now, what is to be kept in mind is that the axis of rotation is the z axis. So, the axis of rotation that we have considered is the z axis, and this lies in the mirror plane. Okay. Now, if you imagine doing C4z on sigma d, okay, then what you will end up with is sigma yz. Okay. So, what you saw is that this C4 operation, in some sense you can think of it the following way. You can think that this C4 operation took this mirror, this sigma xz mirror, which is shown in blue, and converted it to this sigma d mirror. Okay. So, this is the operation, this is like a C4 z operating on the mirror itself. Okay. And you can only do this when the axis of rotation is in the plane of the mirror. Okay. So, and if you do this again, if you now operate C4 on this mirror, you will get a mirror along the yz. Okay. And you can continue and you can show all these, you can generate more mirrors. Okay. What is to be kept in mind is that while we did this, okay, so you can actually show that if you had a Cn axis and a mirror containing Cn, okay, then we will get n minus 1 more mirrors. Okay. So, if you do by C4 you will get this, if you do again by C4 you will get another mirror that looks like this. So, so basically these additional mirrors are generated using the C4. Okay. So, if you just had a sigma xz, you operated by C4, you will get sigma d, and then you operate again by C4, you will get this other mirror that is same as sigma yz. If you operate it again, you will get this other mirror which is another sigma d. Okay. So, from this one mirror you generated three other mirrors. Okay. So, same way if you have a Cn axis and a mirror containing the Cn, we will get n minus 1 other mirrors. Okay. Now, what is to be kept in mind is that these are very simple operations that we considered, okay, where we could actually identify the product easily. So, and we could also classify them in terms of, we could just by visually inspecting we could see that this product turned out to be the sigma d. Okay. Just by visual inspection of this of what we got. Okay. You cannot always do that. Sometimes the product of operations, it is not obvious what the combination of symmetry operations is. Okay. We will leave this here. Okay. Now, I will just mention, I will just talk a little bit about translations as symmetry operations. So, what I want to say is that so crystals have a translation symmetry. Okay. What is the translational symmetry of the crystal? Okay. So, if you take an arbitrary point, okay, so if you take x, y, z, or actually I should say it differently. So, if you translate translational symmetry for translation by by a Bravais lattice vector. Okay. So, if you translate it by this vector, okay, which is the Bravais lattice vector, or in some cases it can be the unit vector of the crystal by the primitive translational vector, okay, or multiple of primitive translation vector. So, for example, if we consider just a lattice instead of a crystal, if we just consider a lattice, okay, then you know that you translate any point by a vector r, which is given by n1 a plus n2 b plus n2 c. Okay, then you will get where n1, n2, n2, n3 are integers. Then you will get essentially an identical point. You will get the same crystal. There won't be any change. Okay. So, now let us, for simplicity, let us take n2 equal to n3 equal to 0. So, if n2 equal to n3 equal to 0, so we will take the example. So, translate by a, okay, does not alter crystal. Okay. So, this is actually the definition of the crystal, that definition of the crystal and these primitive translation vectors. Okay. Now, suppose so in fractional coordinates, so this is translation by one fraction. Okay. So, one fraction along a direction. Okay. That means, so instead of saying translation by a, you say you translate by 1 along the a direction. Okay. And then this is in fractional coordinates. Okay. So let us take an example. Suppose you take a square lattice. You take a, let us say a crystal formed using a square lattice. Now, if you translate it by, if you translate every point by a distance a by 1 unit along this direction. Okay. So, if you translate every point by this, okay, you will get an identical crystal. It is very easy to see that. So, now this symmetry operation is actually used to define the crystal. So, the translation by 1 unit, okay, along one of the crystallographic directions is used to define the crystal. Okay. So, what we are interested in is, suppose we translate by less than 1, okay, translation by less than 1 unit. Now, this, it cannot be a symmetry operation. Because we said that A is in some sense the smallest translation vector, okay, that gives you this identical crystal. So, if you translate by less than this, then you won't get it won't be a symmetry operation. Okay. So, the question when we are discussing translation as symmetry operations, so we can ask the question, okay, can we combine fractional translation, that is translation by less than a, which is not a symmetry operation, with other operations to generate new symmetry operations. Okay, so this is a question. The answer is yes, and we will see in the next two class how this is done. Okay, so we will see that this leads to two new symmetry operations called the glide planes and the screw axis. Okay, but we will do that in the next class. So with this, I will conclude this lecture, and here I have talked about combining symmetry operations. We talked about the effect of a symmetry operation on an arbitrary point, and then I also told about I introduced how to think about translation as a symmetry operation. So I will conclude this lecture here. Thank you.